Well, hello everyone. Welcome to another Science of the Times podcast. I'm Tim Colson.
Hi, I'm Simon Khalid.
And Simon, where have you been this week? Because midweek you sent me a video from what looked like the seaside.
Come on, I wasn't at the seaside, so I was at a serious conference in Boulogne. So it was called Diving into the Secrets of Cellular Membranes. But yeah, they did have it at the largest aquarium in France. So it's pretty cool. Got to play with some rays. We got to touch them in the sensory pool, as well as hearing some cool talks.
And why did they choose was there a reason they chose the aquarium, or just because it's a really nice location?
I think it's just a nice location. The lecture room's big enough to hold people, and there's lots of breakout spaces. And I guess it's outside of season. So yeah, but it worked really well.
And you're now actually in Oxford for a few days, are you?
Says the man who was on safari earlier. Yes, I am in Oxford. And so, Tim, yeah, I wanted to say, you look great today. A lot more stylish than usual. What's going on?
Well, this is a jumper produced by Grace and Garbo. And we're delighted to... I thought you were going to be wearing as well to sport these. They're supporting our podcast, and it's an absolute pleasure to be rocking this jumper. And I think, does it make me look thin?
It does. You look great.
So we'll provide details to them in the in the notes below the podcast.
Yeah, if you want to look like Tim, then you'll know where to go.
So one of the things that's come up again and again in our podcast, we had it with the birdsong one when we were talking to Ben Sheldon and Nilo, and we also had it in the protein folding one. Is the use of machine learning in science, and we've kind of rather taken for granted a little bit about what machine learning is.
For sure.
And artificial intelligence is. But it's creeping into our lives every day, isn't it?
Yeah, increasingly so. I think possibly there's no sphere of sort of life or things we do every day which doesn't have some impact of AI or machine learning.
So today, for our listeners, we're going to learn a little bit more about what it is and its history. And we're absolutely delighted to have Chris Summerfield on. And Chris has just published a book called These Strange New Minds, and perhaps you'd like to give us a subtitle and introduce yourself, Chris.
Hi. Yeah, so I'm Chris, and I wrote a book called These Strange New Minds, How AI Learned to Talk and What It Means.
And it's come out reasonably recently, hasn't it?
This month, yeah, so March 25.
And I can thoroughly recommend reading it. You can get it from all good booksellers, and there's an audio version that I listen to, and I learned a huge amount. And so the book starts with the history of AI, but goes on to tell us how it works, to tell us major advances, and to talk about the future. So should we start at the beginning?
Yeah, I mean, I think I was amazed that perhaps some of the origins date back to the 17th century. Is that right?
Or even before, yeah.
Oh, wow.
I mean, of course, we've been talking about thinking machines for thousands of years. I guess that, kind of you want to put a peg in the ground and talk about when AI started. There's one kind of salient moment, which is with Leibniz. So Leibniz famously invented a kind of like a language for thinking about, or he invented the idea that you could generate a language for processing information such that you might be able to, put in a kind of proposition, and you might be able to crank some handles and get out an answer. And Leibniz never built the machine, although he did build some machines that did some primitive arithmetic. But that idea is really the foundational idea which led us to go on and then build machines that actually did.
What's the date of that?
Is this an exam?
And this is the Leibniz who invented the notation that we use for calculus. So the guy who was alive at the same time of Newton.
That's right. That's late 17th.
Yeah, exactly. Okay. Yeah. And so, but actually, before we dive in a little bit deeper, you're not really a historian, are you? How would you describe yourself? A neuroscientist or a machine learning expert or a linguist? I mean, your book covers all of these topics, but how would you describe yourself?
Obviously have a different answer depending on who's asking the question. But no, so I trained as a cognitive scientist or cognitive psychologist. And at various points in my career, I got into neuroscience. So I've done work trying to understand the brain. Then around about 2010, when the deep learning revolution was just sort of kicking off, I got involved with a research company called DeepMind and became sort of initially a neuroscientist in that company, and then got more and more involved with actual AI research. And more recently, my work has touched primarily on like social, economic, and political implications of AI, and I've been doing a lot of work in AI safety.
Wow. Okay. So you've jumped around. That's not the right thing, but you've moved from field to field and actually expanded to, and that's how you've got this ability to have a really quite a broad oversight on what AI is and how it and how large language models in particular function and operate and the opportunities and threats they pose.
Well, when large language models kind of like entered the public consciousness and everyone started to get excited, I thought, well, there's probably room for a sort of prolonged discussion that tries to encompass the technical aspects, like how do they work, the cognitive aspects, like how are they similar or different to us, and then the social aspects, like what do they mean for wider society, what's going to happen in the future, those types of things. And I thought there are probably quite a few people who could give a reasonable overview of those three topics, but they're probably all really, really busy building AI. Whereas I thought, so well, maybe I could step in whilst they're busy solving AI. I could just write about it.
So that was a conscious decision to sort of you found a niche, sort of thought, here's a niche and I can make a difference here.
No, definitely. And I did, you hear so much talked about these models, right? ChatGPT is on everyone's lips, and the actual level of kind of like public understanding of what the models are and what they do is, I think, very, very limited. I think if you look even like beyond the developed world, so we forget that ChatGPT doesn't just exist in Europe and North America. There's millions of people in India who are using ChatGPT actually primarily in kind of voice mode, and it's totally unclear actually what people who have very different access to education, what they think about it, what they know about it. It's actually unclear in some cases whether they even understand that it's artificial and not natural.
So let's go back to the history. Leibniz was kind of one of the first people to talk about it. When was the first real attempt to actually build a machine? So Leibniz, I think, kind of an artificial mind, as it were, artificial intelligence. So Leibniz thought about it, but he was too busy inventing calculus.
Too busy. I think, kind of in the early part of the 20th century, lots of the foundational ideas happened on paper. So, of course, Turing and his famous papers. And then during the Second World War, there was an urgent need to turn equations into something that actually solved problems. And of course, the big problem that was solved there was the Enigma, cracking the Enigma code, which wasn't really done with a form of artificial intelligence. It was done with a form of brute force search that used Bayesian probabilistic methods, I guess. But, it's I think it was what that step did was it told people about the practical, that practically large computational power could be used to solve big problems. And I think that's the first case in which that was actually, that actually happened. So it was really in the 50s that things actually got going. So famously, I'm sure you will have heard, there was this meeting called the Dartmouth Conference, which happened in 1956, and attendees at the Dartmouth Conference, I mean, it's interesting, talking about the multidisciplinary and all the ideas that feed into this field, as you said right at the beginning, kind of like AI is touching on structural biology and it's, touching on, aspects of ecology. So AI has always been a multidisciplinary endeavor, and attendees at this Dartmouth conference, which really got AI going, were statisticians, mathematicians, psychologists, electrical engineers. So people from a broad range of disciplines. And they kind of got together and said, well, let's try and put these ideas about how to build intelligence, let's just do it. And they got a grant, and they estimated, kind of like, I'm sure you're familiar with writing grants, you sort of de rigueur to sort of overpromise a little bit.
Never happens in biology.
We'll solve this problem in 2 to 3 years. So they got a grant from, I think, the Rockefeller Foundation, and they promised that they would build a thinking machine in 2 months. They thought it would take maybe 10 weeks. I think they thought it would take them 10 weeks. So they sort of holed up in this, in I think a sort of second floor of a kind of don't know what building it was in Dartmouth. And apparently it's very hot. And they just chatted. They just chatted all summer. And the one thing they did achieve, I mean, many things were achieved, but the one thing they did achieve, aside from making friends, was they coined the term artificial intelligence in that summer in 1956. There's actually a guy called John McCarthy who attended the conference, who was a fellow of Wadham College here in Oxford, who is attributed with coining that term that summer.
But they didn't deliver on the grant in terms of producing a machine after 2 months.
Well, not after 2 months, but
Yeah.
I guess that the most productive outcome, aside from the sort of intellectual foundations and so on, was the getting together of John Newell and Herb Simon. Sorry, Alan Newell and Herb Simon. And Newell and Simon became the kind of famous duo who worked on symbolic artificial intelligence throughout the 50s, 60s, and 70s, actually into the 80s, when they were recognized for everything they'd done with winning the Turing Prize, which is sort of like computer science's Nobel. And just in the late 50s, I don't remember the exact date, but they built the first kind of what I would call the first kind of superhuman system. So, we think of superhuman systems as being maybe ChatGPT is superhuman, or we can argue about that, or maybe, kind of Deep Blue playing chess is superhuman. But actually, they built a system called the logic theorist, which was it's a machine for proving theorems using logic. And in the tradition of the time, what it did was it came equipped with a set of primitives, which are logical operations. And, you could put in propositions and, it would essentially verify those propositions through a sequence of steps. And what you'd get out the other end was a proof, or if there was one to be found. And they built this in the late 50s. And so they applied it to the theorems in, I think, Bertrand Russell's Principia Mathematica, which was sort of famously impenetrable tome, which took him so long to write and was so complicated that Russell himself, I think, fell out with Whitehead, his co-author, and went mad. But the the logic theorist found a proof which was more elegant and simpler than one of the proofs that Russell and Whitehead had come up with in that book. So pretty impressive for 1950, whenever it was.
So just in terms of practicalities, just I've been thinking about perhaps our listeners are lost with sort of things like primitives and these sort of ideas. As say I'm a user and I want to use this device, what would I put into that and what would come out, if you see what I mean? Yeah, so
it's probably a bit, it's not something that you would kind of think of as, it's not something you would sort of query for an answer to, how do I get from here to Charing Cross, or which is the best novel by Jane Austen to read. It's, we're thinking about something that is, the inputs are a pretty abstract formalization of some contention, right? So, I'm not a logician, but, you can express in the language of mathematics or logic, you can express propositions.
Yes.
And then you can obviously transform those propositions via a series of lawful steps, which are legitimate transformations like you do when you're solving equations. And, obviously when you're trying to prove a theorem, then, kind of what you're trying to do is you're trying to take some proposition, you're trying to turn it into a form which establishes, a basic equality or some basic form. So what the model was equipped with were logical processes which would allow it to do those legal transformations.
So a little bit sort of like, if this is true, then this is the next step, and then this must be true. If this is wrong, then this can't happen.
Yeah,
and so you sort of build sequentially on these, or perhaps it doesn't have to be sequential, perhaps it can be parallel, but you build on these and come up with some kind of yes or no, this is possible or this is not possible.
That's absolutely right. And one way of thinking, so this is sort of one route to, if you like, knowledge synthesis. So you can synthesize new knowledge by applying rules, like lawful rules, to data. So, kind of the simplest example that every sort of, schoolboy learns is like, if Aristotle is a man and all men are Greek, then Aristotle is Greek. That's not the exact example that they learn, obviously. But kind of the inference that you can make from the premises is it's not something that you knew beforehand, but you can draw that inference by applying the laws of logic.
And so following that breakthrough, what was it called? The
logic theorist.
The logic theorist. Once that had worked and had kind of come up with a more elegant proof than living mathematicians, that presumably gave people working in the area, that the emerging area of artificial intelligence, the belief that they'd probably crack language quite quickly, the way that we speak to one another and come up with rules. And I think that then began what became quite a heated debate in linguistics about whether there were fixed rules that we would be able to identify, or how strict those rules would be and how flexible they were. Have I got that right?
Yeah, absolutely. So, kind of like, if you can think of logic as a formal language for expressing things that might be true, like, Aristotle being Greek. And of course, but we don't generally communicate in logic unless we're, Dr. Spock.
We do on this podcast.
Oh, absolutely. We use logic along with like a gentle dose of humor and many other things. But yeah, so we communicate in natural language. And so the question, language is obviously this remarkable, it's the precursor capacity unique to humans, which is the foundation of, everything that we have achieved essentially, right? So our ability to exchange information with each other is the foundational skill which has allowed us to cooperate and build advanced civilization. So obviously it's very exciting if you can think about extending that principle of generating new knowledge through a logical language, extend it to a computer that is actually capable of language. And so that idea is actually really old as well. But round about the same time as the Dartmouth conference, it was there was a kind of new energy was injected into that idea by Noam Chomsky. So Chomsky famously, kind of joined I think first Harvard and then MIT, or the other way around, I forget. But wrote in the 1950s his first book, which kind of sort of laid down a gauntlet to linguists, which was, kind of like, let's try and define the set of rules which allow legal transformations of sentences into their equivalents, right? So, kind of like, I think of a good example. So, kind of like, you have, yesterday I went to the shops. Kind of the shops that I went to on yesterday were down the street. Like, those are not equivalent sentences, but they have a kind of correspondence to them. If I were a linguist, I'd probably have some good examples at my fingertips. But
you have some in the book. Yes, yeah.
But the idea is that kind of language is a system of meaning. This is Chomsky's view. We can debate this view, but language is a system of meaning which conveys truth, and that truth is somehow locked up in the way that we use syntax to structure information. And if only we could divine those rules of syntax in the way that we kind of like think we worked out what the rules of logic are, then we could build a computer that could speak just like us. That was the idea.
And it was assumed that they'd be able to crack that problem quite quickly. So once, because Chomsky was, a huge figure in linguistics, I think the most cited researcher on the planet, or up there.
He's the world's most cited living scholar.
Yeah, which is isn't that amazing? Yeah.
It's astonishing. Yeah,
I'm like 1/1,000,000th of a Chomsky, I think. and I think a lot of people thought, well, that's a very sensible framework to work in. We should be able to discover these rules really quickly. But there were some people who disagreed, I think. Is that right? Or disagree? Yeah, and the empiricists. Yeah.
I mean, one way of thinking about the debates that overtook the field in the later part of the 20th century is that they're just a continuation of a kind of intellectual battle that's been going on ever since, kind of Plato and Aristotle, over whether the nature of reality is best thought of as kind of disclosed by, satisfying a set of unobservable but true by definition rules, or whether it's the kind of messy reality which we perceive at the sensorium, right? Perceive with our senses. And so Chomsky's very much, he's in the Plato camp, right? So he's all about rules. And, his idea is that, as we said, if we can only solve the problem that every 4-year-old has solved, right, which is to work out what those set of transformations are, then we've cracked language. But there's, kind of an alternative perspective, which is, we also learn language. We learn language by observing lots and lots and lots of data. And Chomsky was very rapidly criticized by people who believed that it would be possible to learn language, not by working out what the rules were, but just by exposing computers to lots and lots of kind of statistical associations between words, so that they kind of knew that, in the sentence, the cat sat on the blank, that Matt was more likely than jellyfish, for example.
But so if that latter one is true, then it would reach a limit at some point, I guess. Because if you learn, you'll be dependent on the data that you're learning from, and then at some point, maybe am I getting this wrong? Maybe it stops being predictive, or it stops doing something unexpected, because that's not what it's learned. Is that right?
Well, so, there are obviously lots of situations where if you're exposed to lots and lots of data, that maybe we're getting ahead of ourselves here, but like you exposed to lots and lots of data, you can obviously, a learning system can encode that data, right? Mm-hmm. So if you're Novak Djokovic and you play tennis for 10 hours a day, then guess what? You get really, really good at tennis. But that you don't just get good at the tennis shots, the exact tennis shots that you've played before. You get good at actually, or the opponents that you've played before. You get good at actually playing like literally anyone, even if they're left-handed, or, kind of like have an unusual net style or whatever. And that ability to take what we've learned from one set of data and apply it to other data that is quite similar. Psychologists and machine learning researchers call that generalization. Sometimes they use the word transfer. And so the hope was that by applying statistical methods to language, a computer model, would learn enough about the kind of like underlying structure of the data that it would be able to generate and understand new patterns, new sentences, for example.
And that's basically what ChatGPT has done.
That is basically what ChatGPT has done. And, but like most people thought that was basically impossible up until about, but varying degrees of impossibility. I certainly thought it was probably impossible till about 2020, 2019. Some other people more far-sighted than me thought it was impossible till about 2000. Some people, have never thought it was impossible, and they built ChatGPT. So, yeah.
And so the statistical model underlying it, it's known as an artificial neural network. Is that right? And
That's right.
And it's broadly or roughly structured much like the brain works, in terms of the fact that there's lots and lots of connections between nodes or between points, and those connections are either the way that why don't you explain it? But that you train the model, so some of those links become stronger and some of them become weaker. Is that right? So
that's right. Yeah, absolutely. So there's different ways of thinking about this. I mean, maybe the simplest way to think about it is like to think about what it actually means to understand the statistics of language. So, the words that we produce are not random, right? Mm-hmm. And what that means is that the probability of any one word following another word can be higher or lower depending on what those words are, like my cat sat on the mat example, right? So the principle is that if you had a system which was able to kind of somehow learn what all of those transitions were, then so it knew the probability of every word conditional on every other word. And here, we can think about word A following word B, but we can, word B following word A, but we can also think of word D following words A, B, and C. So now you have like a probability, a conditional probability, which is conditioned on the precise sequence that you have A, B, C. Right? And so you can get some quite complicated like transition functions that have to be, that could be learned. Okay, so the question is, how do you build a system that does that? And actually the first systems built right up until, kind of well into the 21st century, literally just memorized the frequencies of those transitions up to, kind of like 5 or even 7 words. This is called a gram model, an n-gram model. So, a bigram is just 2 words. But by the time you get to like 7 words on the fly, like actually, if you sample from those probabilities, so you generate, you pull words out with the probability that is given by your transition, your encoded transitions, then you actually get something that sounds quite a lot like English, or quite a lot like the language that you're sampling from.
But doesn't make much sense in terms of content.
Well, so the sentences sound kind of like, they sound a bit, Jabberwockian's not the right word, because they contain words that we would recognize, but they're just completely devoid of meaning. It's like as if I started to spout Shakespeare at you, kind of like, "Oh, ye in the city with thy aunt, falling from the balustrade, and was breakfast."
It's a bit like me down the pub after a few beers at the end of the evening.
Not even a few.
So that approach was successful at generating sort of plausible looking sentences, but not at generating anything that actually had any meaning that you or I would recognize, at least. So this meant that all the kind of, initially all the sort of Chomsky, kind of adherents of Chomsky who believed in rules, they were like, well, of course it doesn't have any, it doesn't make any sense, because you haven't put the rules in. There's no rules. It's just statistics. And so Chomsky said, if you don't build in the syntax, it's like kind of trying to do maths by like, just sort of guessing what's going to come next. It would be like ridiculous, right? You got to do maths by doing maths.
So I guess, again, for the readers, so the rules would be, as you said, the grammatical rules, for example, like we have to have an adjective, we have to have a noun, for example, and build those in, and maybe they have to come in a certain order even.
Yeah, so here to do justice to your question, you'd need a real like computational linguist, but they're things like, they're basically the transformation rules that can make sentences like approximately equivalent through, changing like changing active to passive voice, active to passive voice. I can say anything that's said in the active voice, I can say it in the passive voice through kind of like through a lawful transformation. And it doesn't matter what the words are, it's the same transformation, right? So Chomsky, what his life project, if you think about it, before he, became an anarchist, his life project was to write down an exhaustive set of those rules. And the statistical approach remained kind of like deeply unfashionable for years and years and years. So here, sorry, Tim, about 10 minutes ago, you asked me what a neural network was. And so
that's right.
Here's a good time to answer.
And this is why you need to remember so many steps back in a sentence, right? In order to make predictions.
Exactly. Well, we'll get to that. Yeah, exactly. Yeah. So around about 2000, neural networks, got a little bit better. And it's not just that neural networks got a little bit better, but the data they were trained on got a little bit better. So let me explain what a neural network is and how it works. So broadly, instead of just sort of memorizing the frequencies of those transitions, what you can do is you can take a piece of computer code, and that computer code really just has a very large number of what we call parameters. So the parameters are just like ways that you can adjust how your one set of input numbers gets transformed into a set of output numbers, essentially. So, we're all, if you ever use mathematics in your work, you'll be, as I'm sure you do, you'll be familiar with what a function is. So a function is just a way of like mapping, one set of data into another set of data. And, the parameters will determine exactly how that mapping happens. So if you've got a polynomial function, then, kind of like if you have two parameters, then it will transform data linearly. It'll just be an affine transform. And if you have more parameters, you can make it quadratic or cubic or whatever. And so a neural network is just an extraordinarily complex and fancy way of like building a function which maps one set of data into another set of data. And the trick is that rather than setting the parameters by hand, which if you've got like a million of them would take a really, really long time, what you do is you give the network some kind of objective. So you give it some way of quantifying whether the mapping
Is good
from
or
input
bad,
to output is good or bad. And then you do an adjustment process where you adjust to all the parameters by just a tiny little bit so that the next time it makes that mapping, that it's a little bit better. And so this obviously, this is, you would naturally think of using this for, I don't know, kind of solving problems where you think about numbers, right? So it's just numerical problems, like language is obviously a language problem. So how do you do this? And this was part of the challenge, right? It's like people didn't really know how to kind of put language into a neural network. Because if you can put language into a neural network, you've got a mapping problem, which is the cat sat on is the input and Matt is the output. Yeah. And so around about the year 2000, they figured out a clever way to turn words into numbers in a way which was really useful to neural networks. And that then allowed them to, so that's simultaneous with the fact that the internet had been invented. And because the internet was invented, suddenly there was a lot of digitally available text. And so you could have corpora. So corpora is the plural of corpus, like a body of text. You could have corpora of like millions and millions of words. And even by the year 2000. So you've got two things. You've got neural networks. Suddenly someone's worked out how to turn language into numbers, to use neural network as a prediction problem. You've got big bodies of data, and computers were obviously, still sort of Stone Age by comparison today, but they were a lot better than in the 1950s and 60s. So you put those three ingredients together and you start to get takeoff on what's known as NLP, or natural language processing, as a subfield of machine learning and AI.
I think it's fascinating, and not just here, but I mean, I'm sure we find in all our scientific endeavors that, as you said, this idea started ages ago, years and years ago. But it has to have the technology, the ideas, perhaps the people. So many things have to come together. As you've said, it has to be these three ingredients, and then it takes off. But the foundations and the birth of the idea was somewhere in the past.
Absolutely.
And
so, if Leibniz has had access to GPUs,
yes,
who knows where we would be today, right? He just didn't have the technology or the tooling to turn his visionary ideas into reality. So, they remained sort of like scribblings on a page. But many years later, that intellectual tradition has ultimately borne fruit. And that's what we're living through today.
But there was another important step, wasn't there, which was the development of this thing called the transformer in 2017.
Yeah.
And that was a major. People at the time didn't realise, I think, quite how important that breakthrough was. If I remember your book correctly. And in fact, it wasn't even accepted as a talk at the conference. It was a poster, which made me laugh. No one really noticed it, but now this is an unbelievably, people worked out how to use it and how important it was. Yeah. And I mean, very briefly, without going into too much detail, that what does the transformer do that sort of allow the outputs of neural networks to sound so convincingly like you're talking to someone who's human?
Yeah. First, before explaining that, let me just say that. So we were talking about Chomsky being the most cited living scholar. So I don't know how many citations he has. It's several 100,000. But the Transformer paper from 2017, which was made by Google Brain, but published by Google Brain, and as you say, was rejected for the main machine learning conference of that year. I think it's now been cited more than 150,000 times, just that one paper. So yeah, that would have been a good paper. If you got the email saying, would you like to be a co-author on this paper? Yes. That would have been a really good one to say yes to.
Be pretty good for ref impact.
So let me answer your question. So, a neural network, obviously, needs to be, as we said, kind of, you want to predict the next word. Your ability to predict the next word is going to depend upon how far back in the sentence you can go. So the cat sat on the is easy, but you can imagine that I reference I'm talking about something, and then kind of, as probably is happening here, go off on some tangent, but ultimately you want to get back to where you were. So in order to make sense, what I say now ideally is going to be contingent on maybe things that were said, I don't know, minutes or even hours ago. So the tools that we had, the neural network tools that we had for doing that prediction up until about 2015, 2017, what they did was they took each bit of information and they kind of passed it forward in a single step to themselves. So they had a state, like that's the state of, kind of like all the activity in these units, which are controlled by these parameters that we were talking about. And it got passed forward and passed forward and passed forward. But what that meant is, because, just like when you play Chinese whispers, if you pass a message forward lots and lots of times, it tends to get corrupted and gets lost. So that means that information which was relevant but happened a long time ago kind of gets erased and can't be used for the prediction. But what the transformer does is something completely different. So it takes in, instead of passing the information step by step, it takes in a huge, great chunk of text in one big gulp. And what it does then is it says, okay, so it's still got lots of parameters, but now the algorithm is a bit different. And what it does is it learns which bits of a input are relevant to which other bits for making a prediction about what comes next. So, if you have things like, John was going to the shops, he blah, 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 blah. And then, kind of there's another piece of text which needs to reference John. You know that it's John that's going to be referenced because it was he rather than, some other pronoun or some other part of speech. And that type of, that learning the relations between different parts of the input turns out to be absolutely crucial for language. And actually, it turns out to be absolutely crucial for almost everything else as well. So for language in particular, because our sentences are not linear, right? What we say, what we mean, can often be kind of retrospectively revealed by what we say later on in the sentence. And so the transformer allows for all those kind of links to be learnt, and that makes it really, really good at prediction.
So it's a little bit like taking the context with you as you move the information.
It is, yeah, and it's literally called the context. So the input to the transformer is called the context window, and you'll hear tech companies boasting about their new model having a context window of 1 million tokens or 2 million tokens. Right. A token is like a sort of part of a word, and that is basically what they're saying is, kind of that's the size of the mouthful of text that the model can take at once. And to give you some kind of indication of what sort of volumes of text we're talking about here. So kind of like I think I can't remember exactly what the statistics are, but there's a few kind of like there's a few 100,000 tokens in a book, I think, or 100,000 tokens is approximately book length, I think. So if you're thinking about 1 million token context length, this is a system that can then in one go simultaneously all at once gulp down 10 books worth of stuff. Yes. So that's a lot of information. And what it's learning, of course, are links between all of the bits of information in all of those 10 volumes of the Encyclopedia Britannica or whatever. So it knows how everything relates to everything else. And that is what gives the transformer its power.
And that's the reason that they're so convincing when you're talking to them and you might think you're talking to a person.
Well, absolutely, because they've been trained on lots and lots of data, most of the internet, and they've been trained in such a way that they understand the relations between different bits of text that people have generated. And so they're able to simulate the generation of that text in ways that are very, very plausible.
So they're built up on a big statistical framework. Can they then spit out, and have they yet spat out the rules that Chomsky's looking for?
Well, actually, so not exactly. I mean, you can ask. So they've read they've read a lot about computational linguistics. So you can, of course, ask them all about Chomsky and his transformational grammar. And ironically, ChatGPT will be perfectly happy to tell you with, reasonable accuracy, at least certainly so it appears to me. The question, I guess the deeper question is like, in some sense, although they're just a sort of statistical prediction machine, have they kind of implicitly learnt the rules somewhere in their brain, those rules that Chomsky was looking for, just like in, a 4-year-old's brain. The 4-year-old has implicitly learnt the word. They haven't learnt the rules of syntax by being sat down and rapped over the knuckles every time they got their grammar wrong, although that might happen, at some of the time. They've learnt them implicitly. So do these models learn the same? There is evidence that they do. So, you can, it's a bit complicated to describe, but you can kind of peer inside their brains and do the types of analysis that you might do if you were a neuroscientist.
Yes.
And sort of understand, kind of like how do their brains respond when you present things that have different syntactic rules? And the answer is they respond, you can see evidence that their brains, of course it's not a brain, it's a neural network, but their brains are responding almost as if they had been taught those rules.
So what can't they do yet?
Yeah, that's a hotly contested question.
Right.
Probably requires many layers of qualification. So, there are obviously lots of things that the models just empirically can't do. So they're really bad at tennis.
I might be able to beat someone at tennis finally.
So ChatGPT, you wouldn't want to challenge it to a game of tennis.
Of not.
Probably also wouldn't be that much fun at a dinner party. If you took your laptop and just sort of sat it there and, put it on a chair, it probably wouldn't be the most scintillating guest.
It might be more so than some of my colleagues, to be honest. But
And people are falling in love with these with the various GP.
People are, yeah.
GPTs, aren't they?
So I think we have to distinguish the question of like, there's a question. Yeah, they are.
really?
Okay,
Yeah. I know, it's sad. Yeah, and worse than that. I mean, you talk about a case where someone committed suicide after talking significantly. I think it was you in your book. You talked to.
Absolutely,
Yeah,
and there was
just
another
awful.
case
Yeah.
more recently
Yeah,
as
no,
well, beyond the window of my book being published. But yeah, no. So yes, not
They
very
can be
scintillating
convincing,
not very scintillating as a dinner party guest, but you can train the models to do lots of things that kind of like you wouldn't necessarily get out of ChatGPT in its kind of like out of the box form on OpenAI's website or whatever. So I think the important point here is we need to distinguish between what can the models do and what could they do in principle. So we can write down set of things that they can't do, but the question is like, where is the limit? Like, what could they in principle do? And Tim's example is a good one. So it turns out that there are lots and lots of websites where you can go and, they're versions of ChatGPT, but rather than trained to, kind of like answer useful questions about, health ChatGPT is not trained to answer questions about health. Useful questions about, general knowledge.
Yes.
They're trained to interact with you in kind of like, personal or even intimate ways. And the story about how these websites came about, or the first one of them, is actually quite fun. So one of the best known ones of them still is called Replica. So Replica with a K. And it began because there was a woman who's a sort of kind of a software developer living in Moscow, and her sort of best friend and business partner was kind of killed. He was very sadly run over in a Moscow side street and was killed. And she was distraught, but she had like nearly a decade's worth of text-based correspondence with him. So they, texting back and forth all day, great friends, commenting on their lives or whatever. And so she wondered, well, what happens if I train an NLP system, a neural network trained to process language, train it on his texts? Can I then use it to generate data, which is kind of just like a bit like my, this dead friend that I'm missing so much? And it turned out it worked really, really well. So she thought, okay, let's make a business out of this. So she did. So that's what Replica originally began. It was an idea. The idea was that you could kind of like, it's it's sort of like linguistic cryogenesis. You know, you could kind of like, you could kind of freeze your personality as expressed through language in text form. And then, you know, if you were no longer available, others could continue to enjoy you. You might think it's a bit creepy, but, you know, clearly there's a market.
And I guess a more sinister use of that might be just to mimic people and create...
we can talk about safety. So, of course, like there's a huge issue around safety with AI being used for impersonation, because literally it is a tool for impersonation. But the funny story about Replica is that what happened was that, so of course, you know, kind of people uploaded some of their data to start, you know, but then they had to, of course, for it to be self-sustaining, they had to continue to train on the data which was available on the site. So what people did was, naturally, a subset of people started to, like, you know, get a bit familiar with the AI system. And so it was trained on this data, so it started to be quite familiar back. And because it was quite familiar, people got even more familiar with the AI system. And so people started to kind of like, you know, engage in kind of like sexualized banter, erotic conversation. And so guess what? As they trained the model started to come back. And so you enter this kind of loop of training where the model becomes more and more and more like the users, this is the theme of modern machine learning. You know, it is a mirror which reflects back to us how we are.
A stochastic parrot is a phrase I learned from your book, which I thought was a great phrase.
Well, that's a contested phrase, but it's definitely something that reflects back to us what we put in, definitely. And I think that's partly intended by that phrase. So today, there's an absolutely phenomenal number of users of applications which are basically like AI friends, or even, you know, kind of like AI girlfriends or boyfriends. They're very popular.
So I mean, we're kind of running out of time now, but we should just a little bit about, you know, where does AI go next? What's it going to be? What are these large language models going to be doing for us in 5 years' time, 10 years' time? Are they going to become functional personal assistants? You know, are they going to put all the secretaries, all the personal assistants out of jobs, or is that going to be a step too far? Are they going to gang up on humanity and take over the world? Are they going to make life better or life worse? Well, I mean, it's an amazing tool. It's, you know, it's a fantastic tool, but it is a tool. It still makes mistakes. It's great. I mean, the way it deals with language is just remarkable. But clearly, it's not human. It's not conscious. I have no doubt that it's not it's not conscious. It's not sentient. Are they going to get to that point, do you think? As the expert, where do you think they're going to go? Well, and we'll play this back in 10 years' time and have a good laugh.
Like, can you please turn off the recording to spare my embarrassed future self? These are the questions that everyone is asking.
Of course.
So there is no doubt. I mean, I can try and say the things that I believe firmly. So there's no doubt that we're living through a remarkable time of transformation. So there are some people who think that AI is basically all kind of like hot air invented by the tech companies. It's a very famous, actually a linguist who's got a book coming out called The AI Con. The argument being that, you know, it's all sort of like a con invented by the tech companies to inflate their share prices, and, you know, kind of like actually there's nothing to see here. So I firmly believe that that's not the case. Like, these tools are incredible and they are getting better. The question is, like, what does that actually mean for us? And I think that here you've got a huge disconnect. So on the one hand, you have people in the tech world who are extremely excited about the rapidly advancing intellectual prowess of these tools. But the things that they're measuring them on are things which are probably not all that useful in the real world. So they do measure them on some things that are useful. So, you know, kind of like things like, you know, passing law exams or biology exams. Biology exams, I'm not sure how useful biology exams are. Are they useful?
When I set exams, I run the question through ChatGPT, the latest model that's out there. And if the model is hopeless at answering it, I set the exam question.
Right. That's probably a very good strategy to use. So, you know, general knowledge is obviously useful. But if you think about, you know, what would actually transform, you know, for example, the labor market, it's not just something that is really good on, you know, capitals of the world, or knows, you know, can name the periodic table backwards, or even that is good at maths and software engineering. I mean, clearly, you know, being good at maths and software engineering, very, very useful. But many of the skills that we require in the real world need us to do a bunch of different stuff which we haven't yet seen evidence that the models do. So one is, thinking about taking the initiative, right? So, kind of like we talk about the models are very good at following goals which we set for them. But it's one thing to follow goals which you've been told to do. It's another thing to select goals, what the right goals in the first place, right? And this is often actually the difference between, someone who's in a kind of like coordinating or managerial role and someone who's in a kind of like more executive role, right? It's like, it's actually really hard to know what to do when you get out of bed in the morning. So, many people think that ChatGPT will just, or large models will, they will just naturally get better and better at planning, and they'll just naturally be able to kind of like, form their own sub goals and work out what's the best thing to do. But so we don't know, but I think it's at least plausible to believe that there is a significant algorithmic change or another layer of algorithmic innovation which is needed to make models that can kind of like decide what to do as well as doing what you tell them really, really well.
And I guess in a human context, to know that what the best thing to do would also depend on the people or the people that you're, it's context dependent, right?
Yeah.
So best can mean a number of different things.
Best can mean so many things.
Yeah.
And, kind of there's another normative question, which is like, even if you did have a model that could do that in theory, would you want it to, right? Like what, where do you draw the line between what the model should do and the model shouldn't do? So, if you think of most professional domains, there is a kind of like, think about knowledge work, right? There's a part that is just like, it's very useful just to know a lot of stuff and to make good decisions about the stuff right? So if you're a doctor, that's basically like, your day job, right? And of course, the models are really good. They know a lot of stuff and they're good at reasoning, so they can make good decisions. But that's obviously not all there is to being a doctor, right? Being a doctor is about, making like really sensitive decisions around what is best for your patient that are grounded in some understanding of what that patient wants, of their values, of your values, of like the values of the profession.
Yes.
And, even if the model was able to do that, which, perhaps it will be one day, maybe even it will be able to do that soon. I think, we need to ask ourselves whether that's something we actually want, right?
Yes.
So it's good to hear about that getting up in the morning, because I got up this morning and I decided I was going to rock this Grace and Garbo jumper. It doesn't sound like ChatGPT is going to be able to do that anytime soon.
Not like you do it.
No, but I think it's probably time to wrap this up. So thank you so much, Chris, for coming along and explaining a little bit of the history and a little bit of how machine learning and AI works, ChatGPT, these large language models work, and what some of their future holds. And for any of our listeners who want to learn more, I can really thoroughly recommend Chris's book, which is just out, These Strange New Minds, and it's published by Penguin, I think. Is that correct?
By Penguin, that's
And congratulations, it really is a fantastic read.
Thank you so much for having me. It was fun.
Yeah, we enjoyed it too. It's a lot of fun.
But now have you learnt a lot?
Very good. Yes, I have.
Yeah.
No, I think that was fascinating. I certainly had no idea of the history of artificial minds and, the concepts being so old, actually.
I mean, it's kind of, when I was reading Chris's book, it's really impressive how it's kind of mastered language. And these neural networks are astonishing in terms of what they can do. But, one of the things we didn't touch upon in this conversation is, when there's a very defined problem, like protein folding, as we've talked about before, AlphaFold, like playing Go, like playing chess, they can really come into their own and they can solve those problems. They can be incredibly useful.
Protein structures, we should say. Folding is still...
Okay, protein structure.
Folding is still...
But AlphaFold, doesn't AlphaFold tell you what shape of protein you're getting, given the...
It is, but it doesn't give you the pathway to the folding. That's still unknown.
Okay. And of course, in birdsong, it's been shown to be useful. So it's a useful scientific tool, but I'm quite glad that it's not going to completely take over the world within the next year or two. Yeah. Hopefully I'll get to retirement before it does that.
That human touch is important, I think.
No, and it's good to hear that. And of course, it doesn't sense the world as well in the way that we do. It doesn't have eyes and ears, although you do wonder about self-driving cars.
Oh, yeah, indeed. Yeah, absolutely.
So, listeners, subscribe, join us for this, and go and look at Grace and Garbo.
Absolutely.
Okay, have a good week, Simon.
You too. Bye.